Okay, so today we'll be going over the practice exam for Chem 107, practice exam 2. So let's go through a few of these questions. So first we have a series of nomenclature questions. So in terms of nomenclature, first and foremost, let's look in this case. Here we're asked to figure out the formula for sodium oxide. So in this case, sodium is a 1A element, so it has a preferred charge of sodium plus. Oxide, oxygen, is a 6A element, so it has a preferred charge of 2 minus. Crossing the charges, that gives us a formula of Na2O. Any questions on this first example? So next we're moving on to nomenclature, where we're given a formula and we're asked to determine the name. So in this case, we're asked what is the correct name for the following compound. Okay, so MgS. So in this case, we are naming a main group ionic compound. So we write the name of our metal, which would be magnesium. And then we write the name of our non-metal, replacing the ending with IDE. So rather than sulfur, this would be called magnesium sulfide. So it would be any one of these two. Oh no, that's manganese. Let me get the eraser. So this is magnesium sulfide. Does this second question make sense to everyone? Any questions on this second problem? Okay, so let's clear and let's look at the next. So in this case, we're asked what is the correct formula for the following name. So tetracarbon octabromide. So this is textbook covalent nomenclature. Tetra indicates we have 4 carbons. Octabromide, we have 8 bromine atoms. So it would be C4Br8 for this covalent compound formula. Does this make sense? Okay. So let's keep going then. We're dealing with more nomenclature. We're asked what is the correct name for the following formula. This is a covalent compound. So remember, for covalent compounds, you only use the mono prefix if you have a single atom of that element in the second element in the formula. So in this case, we'd name this compound as boron, which is the name of our first element, not monoboron, just boron. And then since we have 3 chlorine atoms, we name this as trichloride, matching the first response. Does this next question make sense to everyone? Okay, let's look at the next problem in the sequence. So we're asked what is the correct formula for the following name. So we have copper 3 oxide. So in this case, this signifies not the number, but the charge. So copper is 3 plus, oxide is O2 minus. We cross our charges, that gives us Cu2O3. So this is a textbook example of variable charge transition metal nomenclature. Any questions? Okay, so let's move on to the next problem in the series. So here we're asked to name a variable charge transition metal containing compound. Lead is a transition metal. So first things first, this one's a little bit trickier than usual in that we have to figure out the charge. Well, if we reverse cross the charges, we get lead 2+ and O-. However, this is not the end of this problem because oxygen has a preferred charge of 2-, so we need to multiply each of our charges by 2, giving us the correct charges of lead 4+ and O2-. Remember, the charges for your main group, metals and nonmetals, must match periodic trends. Okay, so now that we have the charge for lead, we name this variable charge transition metal containing compound by writing the name lead. We then specify the charge in Roman numerals, in this case using the Roman numerals for 4. Finally, we write the name of our non-metal, changing the ending to IDE. So this would be lead 4 oxide, which would be this first response. Any questions on this example? Okay, so moving on now. In this case, we're asked, what is the correct formula for the following name? This time we're dealing with hydrogen-containing polyatomic ionic compounds. So in this case, we have sodium hydrogen chromate. Well, sodium is sodium plus. Hydrogen, we have a single H plus ion. Chromate is CrO4 2-. So then hydrogen chromate, we'd have sodium plus, hydrogen chromate is HCrO4-. Crossing the charges, we get NaHCrO4 as the formula for sodium hydrogen chromate. Does this make sense? Any questions on this example?
The 2-, Professor, the 2- charge is one of them is canceled by the proton.
Exactly right.
Okay.
For each hydrogen atom, your charge becomes more positive by 1 unit. Does that make sense?
Yes, thank you.
Perfect. Okay. In this case now, we're asked to name a hydrogen-containing compound, but this hydrogen-containing polyatomic ion has a special name. In this case, when we're naming this compound, we see what looks like a transition metal, but zinc is a fixed charge transition metal. Thus, we just write the name zinc, and then we write the name of our corresponding anion, which would be hydroxide. So this compound would be called zinc hydroxide. Any questions on this example? Okay. Now we're moving on to a special type of compound. This is known as a hydrate. So first we name our parent compound. We have to figure out the charge. So crossing. We know that the sulfate ion has a 2- charge. So we know we have iron 2+, SO4 2-. So in naming this ionic compound, this would be iron 2. Then we write the name of our polyatomic ion, which is sulfate. Now from here, because we have 2 water molecules, we use the di prefix followed by hydrate. So this would be iron 2 sulfate dihydrate. Does this make sense to everyone? Any questions on the following naming example? Okay. Moving on to the next problem in the series, we're asked what's the correct formula for the following name? So we have barium oxalate heptahydrate. Well, barium prefers to adopt a 2+ charge. Oxalate is C2O4 2-. Crossing our charges, that gives us a formula of barium oxalate as follows. Heptahydrate, hepta implies 7. Hydrate, we have 7 water molecules. So then barium oxalate heptahydrate would be the following. Does this example of hydrate nomenclature make sense? Okay, so let's look at another example. So in this case, we're asked to calculate the molar mass of the following compound. So we just add up our atomic masses. So lithium is 7 grams, hydrogen is 12 grams. We have carbon is 12 grams. We have 2 carbons. Hydrogen is 1 gram, and we have 4 + 3, 7 hydrogens. Oxygen is 16 grams, and we have 3 oxygens. So in total, for lithium oxalate, we have 7 + 12 × 2 + 1 × 7 + 16 × 3. That gives us 86 gram per mole. Any questions on this example? Okay, let's look at another problem. So in this case, again, we're asked to calculate a molar mass, this time for aluminum hydroxide. The mass of aluminum is 27 gram per mole, oxygen 16 gram per mole. We have 3 oxygens. Hydrogen is 1 gram per mole, and we have 3 hydrogens. So we have 27 + 16 × 3 + 3. That gives us a molar mass of 78 gram per mole. Does this question make sense to everyone? Okay, let's look at the next problem in this sequence. In this case, we're dealing with more naming. So in this case, we're looking at an aqueous acid. So in this case, we use the hydro prefix. So this compound would be hydro, and since it's sulfur containing rather than hydrogen sulfide, this would be called hydrosulfuric acid. Any questions on this example? Okay, now we're dealing with another example of acid nomenclature, this time nomenclature of a polyatomic acid. So perchloric acid is derived from H+, perchloric is derived from perchlorate. Perchlorate is ClO4-, so crossing our charges, we get HClO4 for perchloric acid. Thus, we'd select the following answer. Does this make sense to everyone? Any questions on this example? Okay, let's continue moving on and let's look at the next part. So we're asked, what is the mass in grams of 0.15 moles of cesium sulfate? Cesium sulfate, crossing our charges, we get CS2SO4. So then if we punch into our calculator the molar mass for cesium sulfate, we get a molar mass of 361.87 gram per mole. So if we have 0.150 moles of cesium sulfate, to convert from mole to grams, we use the molar mass. We know there are 361.87 gram per mole. So punching this into our calculator, 0.150 times 361.87, and that in turn gives us 54.3 grams of cesium sulfate. Does this example make sense to everyone? Any questions on this example? Okay, so let's do another mass calculation problem. In this case, we're asked, what is the mass of 0.670 moles of potassium carbonate? So if we start with 0.670 moles of potassium carbonate, we know that the molar mass of potassium carbonate in this case,
138.20.
yeah, perfect. So we have 138.20 gram per mole. So we have 138.20 times 0.670. And that in turn gives us 92.6 grams. Does this make sense to everyone? Any questions on this example? Okay, now let's do an example of mass to mole conversions. We're asked how many moles of copper 2 nitrite are found in 40 grams of copper 2 nitrite. So if we have 40 grams of copper 2 nitrite, we know we have 63.5 grams from the copper, 14 grams from nitrogen. We have 2 nitrogens. 16 grams from oxygen, we have 4 oxygens. So adding this up, I got a molar mass of 155.5 gram per mole. So we know in 1 mole of copper 2 nitrite, we have 155 grams. Whoops, I don't need the per mole. I already have it set up that way. Okay, so punching this into our calculator, I get 0.257 moles.
I have a question about this one.
Yes.
I got this one incorrect and I got the same answer as you did.
I can double check to make sure that the tolerances for this problem are correct. I'll be able to see the raw answer that you input and I'll be able to double check it by hand. It may just be that Canvas is throwing an error due to a rounding error in the molar mass. But if you solved it the way I did with this exact calculated molar mass, you should be fine. Did that answer your question?
Yes.
Perfect. Okay, So let's look at this next problem. In this case, we're asked how many moles of sulfur trioxide are found in 71.5 grams. Sulfur trioxide is SO3, which has a mass of 32 plus 16 times 3. I believe it has a mass of 80 gram per mole, if I'm not mistaken.
Yes, it is 80 grams per mole.
So then if we're trying to calculate the moles, we have 71.5 grams of sulfur trioxide. And in 1 mole of sulfur trioxide, we have 80 grams of sulfur trioxide. So 71.5 over 80, that gives us 0.894 moles. Keeping in mind molar masses are precise numbers, and thus will not constrain your significant figures in this case. Any questions on this example? Okay, let's look at the next problem. In this case, we're asked how many molecules of NO2 are found in 3.30 times 10 to the negative 20th moles. In this case, to go from moles to molecules, we're going to use Avogadro's number. So if we have 3.30 times 10 to the negative 20th moles of NO2, we know that there are 6.02 times 10 to the 23rd molecules per mole of NO2. So punching this into the calculator, that in turn gives us 19,900 molecules. Any questions on this example? Okay, let's look at an example of a molecule to mole conversion. In this case, we're going to use Avogadro's number once again. So if we have 1.27 times 10 to the 21st molecules of calcium oxide, we know in 1 mole of calcium oxide, we have 6.02 times 10 to the 23rd molecules. Molecules cancel, we're left with moles. Unit analysis checks out here. And that in turn gives us 0.00211 moles of calcium oxide. Does this make sense to everyone so far? Any questions? Okay, let's look at another problem. So in this case, we're asked to calculate the mass in grams of 2.15 times 10 to the 19th molecules. So in this case, we're trying to go from molecules to moles to grams. So we know in this case, if we have 2.15 times 10 to the 19th molecules of cadmium cyanide, we know in 1 mole of cadmium cyanide, we have 6.02 times 10 to the 23rd molecules. Okay, and then what is the molar mass? How many grams do we have in 1 mole of cadmium cyanide? What
100.
mole? What was that?
164.44.
Okay, perfect. So then punching this into our calculator, we have 2.15 times 10 to the 19th over 6.02 times 10 to the 23rd times 164.4. And that in turn gives us 0.00587 grams. Does this make sense to everyone? Any questions on these examples so far? Okay, so let's move on to another problem. So in this case, we're asked how many molecules are found in 6.52 times 10 to the negative 19th grams of carbon tetrachloride. Okay, so then in this case, we're trying to go from the grams of carbon tetrachloride to the moles of carbon tetrachloride, and then to the molecules. So in 6.52 times 10 to the negative 19th grams of carbon tetrachloride, what is the molar mass? In 1 mole of carbon tetrachloride, we have how many grams?
$153.8 grams.
Yep, perfect. And then from here, we know that there are 6.02 times 10 to the 23rd molecules of carbon tetrachloride in 1 mole. So punching that into our calculator, we have 6.52 times 10 to the negative 19th over 152.8 times 6.02 times 10 to the 23rd. And that in turn gives us 2,570 molecules. Any questions on this example? Okay, let's look at another problem. Let's look at another related problem. So in this case, for the next problem, we're asked how many moles of phosphorus are found in 0.440 moles of P4O10. So we're trying to go from the moles of P4O10 to the moles of phosphorus. If we have 0.440 moles of P4O10, how many moles of phosphorus do we have per mole of P4O10? What's our mole to mole ratio? Yep, 4 to 1. And that gives us 1.76. In this case, 1.76 moles of phosphorus. Does this make sense to everyone? Okay. So let's look at this next problem now. In this case, we're asked how many moles of methane are present in a sample of methane that has 1.75 moles of hydrogen atoms. So we're trying to go from the moles of hydrogen to the moles of methane. So if we have 1.75 moles of hydrogen, we know in 1 mole of methane, we have 4 moles of hydrogen. So in that, in turn, gives us 0.438 moles of methane. Any questions on this example? Okay, let's look at another formula conversion. In this case, we're asked how many moles of oxygen are a sample of barium phosphate. Oh, this one has a typo. We'll just ignore this question for now. Sometimes when Canvas pulls from the question banks, it can do some weird things with formula questions involving chemical formulas. So we'll skip that one.
Thanks,
Okay.
I spent a lot of time on that one.
Yeah, it picks from two columns, and I think this is one case where it pulled two descriptors for oxygen. Yeah, don't worry about that one. Okay, so in this case, we're asked what mass of nitrogen in grams is found in a 3.89 sample of ammonium carbonate. Okay, so we're trying to go from the grams of ammonium carbonate to the moles of ammonium carbonate, and then to the moles of nitrogen, and then to the grams of nitrogen. There's another method that I didn't show in class using mass percentage, but we're just going to use this method because it works pretty well. So if we have 3.89 grams of ammonium carbonate, what is the molar mass?
96.09.
Yep. Okay, and then how many moles of nitrogen are present per mole of ammonium carbonate?
2 to 1.
Let's see, yes. And then looking at our molar mass. Looking at our molar mass, what molar mass are we dealing with?
Nitrogen, which is 14.
Yep. So then punching this into our calculator, 3.89 over 96 times 2 times 14, and that gives us 1.13 grams of nitrogen. Does this example make sense to everyone? Okay, let's look at another problem in the series. In this case, we're asked how many atoms of oxygen are found in a 3.50 times 10 to the negative 20th gram sample of some oxidized hydrocarbon. Okay, so we're starting off with the grams of C4H6O3. We're then going to try to go to the moles of C4H6O3. Then we can go to the moles of oxygen, and then from the moles of oxygen, we can calculate the atoms of oxygen. So if we have 3.50 times 10 to the negative 20th grams of C4H6O3, in 1 mole of C4H6O3, how many grams do we have?
102.
Okay, perfect. And now how many moles of oxygen do we have per mole of C4H6O3?
3 to 1.
Yep, exactly right. And then how many atoms are present in a mole? So how many atoms of oxygen are in 1 mole?
6.02.
Yep, exactly right. Don't forget the 10 to the 23rd though. 6.02 times 10 to the 23rd atoms of oxygen per mole. So we have 3.50 times 10 to the negative 20th over 102 times 3 times 6.02 times 10 to the 23rd. And that in turn gives us 620 atoms of oxygen. Does this make sense to everyone?
Did you round up?
Yes, you have to round up because 619, yes.
Because it's 3.5, so you need to have two significant figures.
3.50, so it would need 3. So it's 620, but with a dot at the end. But Canvas doesn't know how to read that, so it'll, as long as you're in that order of magnitude range, it should be fine.
Would 619 be okay?
It would be incorrect following rounding rules,
Okay.
but Canvas would still probably accept it because there's a range based on how precisely you report your molar mass. Does that make sense?
Yes, thank you.
Perfect. Okay. So let's look at another example. In this case, we're asked, what is the mass of a sample of iron 2 nitrate that contains 2.54 grams of nitrogen? So in this case, we're going from the grams of nitrogen to the moles of nitrogen to the moles of this iron nitrate, and then to the grams of this iron nitrate. So if we have 2.54 grams of nitrogen, we know in 1 mole of nitrogen, we have 14 grams. So how many moles of this iron nitrate do we have per mole of nitrogen? What is our mole to mole ratio?
1 to 2.
Yep, we have 1 mole of iron 2 nitrate, or 2 moles of nitrogen. And then how many grams of iron 2 nitrate do we have per mole? What is our molar mass? $179. Let me check. 16 times 3 plus 14 times 2. And then what's the molar mass of iron?
55.85.
Yep, 179.9 is perfectly reasonable. Okay, so punching this into our calculator. That in turn gives us 16.3 grams. Does this question make sense to everyone so far? Okay, let's look at this next problem. In this case, we're dealing with an empirical formula problem where we need to find the simplest ratio of atoms. In this case, a 4:8:2 ratio simplifies to a 2:4:1 just by dividing all the subscripts by 2. So it'd be C2N1H4. Does this make sense to everyone?
I have a question. Well, why would it be divided by 2?
Because in this case, this gives you the smallest whole number ratio while retaining the smallest coefficients. The reason why we divide by 2 is that 2 is the shared common factor between these 3 values, because 4, 8, and 2 are all multiples of 2. And thus, when you divide by the smallest coefficient, that in turn allows you to simplify to the smallest ratio and generally the smallest whole number ratio. Did that answer your question?
Yes, thank you.
Perfect. Okay, so let's look at another problem. This time we're asked to calculate the empirical formula from the moles. So if we have 0.9 moles of carbon, 1.8 moles of hydrogen, and 0.90 moles of chlorine, So to calculate the empirical formula, what we're going to do is we're going to divide by the smallest number of moles. So in this case, we're going to divide by the moles of carbon. So in this case, we get 1 mole of carbon, 2 moles of hydrogen, and 1 mole of chlorine. This is a whole number ratio, so we don't have to move any further than that. So it would be C1, Cl1, H2. Does this example of an empirical formula calculation make sense? Okay. So let's look at an empirical formula calculation from mass. In this case, we need to figure out the moles. So the moles of carbon, we have 1.656 grams of carbon, and we know in 1 mole of carbon, we have 12 grams. So that gives us 0.138 moles of carbon. We have 0.414 grams of hydrogen. In 1 mole of hydrogen, we have 1 gram. So we have 0.414 moles of hydrogen. And then for oxygen, we have 2.208 grams of oxygen. In 1 mole of oxygen, we have 16 grams. So we have 2.208 over 16. That in turn gives us 0.138 moles of oxygen. Now from here, we divide our moles by the smallest number. So if we have 0.138 moles of carbon, we're going to divide by the moles of carbon. 0.414 moles of hydrogen. We're going to in turn divide by the moles of carbon. And if we have 0.138 moles of oxygen, we're going to divide by the moles of carbon. So then, in turn, this will simplify to 1 mole of carbon, 3 moles of hydrogen, and 1 mole of oxygen, which gives us C1H3O1. Does this example make sense to everyone?
Yes.
Okay, perfect. So we completed our review of the practice exam. So what I'll do is I'll archive this recording.